What I'm going to do now is go through all of the rules mentioned in the content of this section, show you why those are the rules, so do the proofs, and then do some examples applying those rules. So the first rule was the constant rule. So that's if we have a function f at x equal to k. So k is a constant, so it is going to be a number. We use k to represent any number, but an example would be f at x equal 2. So if you have a constant rule, the derivative f prime at x would be 0. Remember, the derivative represents the rate of change. If something is constant, it never changes. So 0 represents the actual rate of change. We can do the same thing using y notation. It's the exact same thing, y equals k, except now we use Leibniz notation, and instead of f prime to represent the rate of change, we use dy dx. But it would still be equal to 0 because we're dealing with a constant. So I'm going to do the proof to show this why this works. So I'm going to go back to my limit because all the derivative rules are based on using limits. It just becomes a shortcut or a way to go around using the limits if things behave the same. So in this case, I'm dealing with the function f at x equals k. Well, because it's a constant, f at x plus h will also equal k, because a constant function means no matter what you sub in for x, the answer is always k. So subbing that in, I get the limit as h approaches 0 of k minus k over h, which becomes the limit as h approaches 0 of 0 over h. Now, I am going to just say that this does equal 0. We technically have the 0 on the bottom, so it looks like 0 over 0. But I can adapt this top a little bit to make it work the way I want to. The top is 0. I can multiply 0 by anything and it remains 0. So I can write the top as 0h because that's still the same. Now I can cancel my h's as long as h isn't equal to 0, and I'm left with 0. So that proves that the derivative of a constant is always 0. Our second rule was the constant multiple rule. So if you have a function, f at x, and it's equal to k times another function, so 2 times x squared, or 3 times x, so you have a number in front and then something to do with x, then f prime is going to be just that constant multiple times whatever the derivative is of this function. I'm not going to work with this one just with the y notation because it'll get confusing. This is the whole convenience of function notation, is that I can define f and g and be able to separate them. If I worked with y's, I'd have 2 y's and it would become confusing. But again, I'm going to do a proof to show you how this works. I always go back to my limit definition for the slope of the tangent or the rate of change or the derivative. They all mean the same thing. So in this case, f at x is k times g at x. F at x plus h is k times g x plus h. I bring it back and sub it in. So I get k g at x plus h minus k g at x over h. Now, not a lot I can do with this because I don't really know what g is, but both of my pieces on top have a k. So I'm going to common factor out the k. So if I take a k out of g at x plus h, I'm left with g at x plus h. If I take a k out of k g at x, I'm left with g at x. And now I have this k. Remember, this k is representing any number, so it's a constant. There's no h involved with that k, so I can actually bring the k out in front of the limit notation. It does not have an h, so k will not change as h goes to 0. But if you look at this, this should look familiar to you. This is the limit definition for slope of a tangent. We learned that f prime at x is equal to the limit as h approaches 0, f at x plus h minus f at x over h. Well, here I have the limit as h approaches 0 of gx plus h minus g at x over h. It's the exact same, except instead of the function called f, we're working with the function called g. But by its very definition, this is equal to k times g prime at x. Now, this probably seems very theoretical right now because we're not working with functions. When I start to do examples after I've gone through the proofs, this should start to make more sense. Our third rule was the sum rule. So if f at x is equal to p at x plus q at x, then the derivative of f is the derivative of p plus the derivative of q. Now, again, I'm not going to work with y notation because it's really useful to have f, p, and q so I can differentiate. But I am going to prove this. So f prime is still the limit as h approaches 0, f at x plus h minus f at x over h, because that's limit definition for the slope of the tangent, and the derivative represents the slope of the tangents. F at x is going to be p at x plus q at x. F at x plus h is going to be p at x plus h plus q at x plus h. And I'm going to sub this in. So I get the limit as h approaches 0, p at x plus h plus q at x plus h minus p at x plus q at x. And this big set of brackets is because I have to subtract all of f at x, so I have to make sure that I send that sign through to all the pieces. I'm going to do that in the next step. And I'm actually going to group the p's together. So that's going to be a subtract p at x, and I put it over there with the p. And then I'm going to have a q at x plus h, and then a subtract q because of the sign, and I put it with the q's. So now, I really have two things. I have p at x plus h minus p at x over h, and I also have q at x plus h minus q at x over h. That's our limit definition, once with p and then once with q. So that is going to work out to p prime at x plus q prime at x. Our difference rule is going to work much the same. That if you have f at x equal to p at x subtract q at x, then f prime, or the derivative of f, is going to be the derivative of p subtract the derivative of q. I'm not going to work through this proof. It's essentially the same thing as this one, except you have your subtract there, and then your subtract, but you'll also have subtract, and the signs will work out, but it does end up being this limit minus that limit. So when you collected all your like terms and moved things around, you would just have a subtract in there. And the last rule, which is the power rule. So if f at x is equal to x to some power n, so some exponent, then f prime at x is, this exponent comes down in front and multiplies, so n times x, and then you drop your exponent by 1. So whatever n was, you subtract 1 to get your new exponent. This one, because I don't have multiple functions, I can also work in Leibniz notation. So if y equals x to some power n, the rate of change, delta y over delta x, or shortened to dy dx, the exponent comes down in front, multiplies, and then the exponent that you're left with is 1 less, so n minus 1. Now, if you're interested in the proof, you can work through it. It is quite a long proof though, but on page 134 of the text, you can read and look at the proof for that one. Because what I really want to start doing are some examples, because that's going to show you that we use these rules. We don't really have to think about them, but we do use them. So f at x equal to 5. 5 is a constant. There's no rate of change. so I know f prime at x equals 0. So whenever you have a number, the derivative is 0. So as long as there's no variance or variable, so no change, the rate of change is always 0. So example 2, if y equals pi by 2. Don't be fooled by pi. Pi is a number. It's 3.14. So this just represents pi divided by 2. It's a constant, so the derivative is 0. And I'm going to match my derivative notation to what I'm given. Up here, I was given f, so I called the derivative f prime. Here I'm given y, so I'm going to call the derivative dy dx. Example number 3, f at x equals x to the 7. This is going to be my power rule. The power rule says the exponent comes down in front and multiplies, and then you drop your exponent by 1. So 7x to the 6. When I have g at x equal to 1 over x to the 3, I'm actually going to change how I think about that before I do my derivative. 1 over x to the 3 is really just x to the negative 3. I can represent the division as a negative exponent. So now, if I follow my power rule, the negative 3 comes down in front, so I do negative 3 times x, and then I subtract 1 or make my exponent go 1 lower, so my new exponent is going to be negative 4. This is an acceptable answer. Sometimes you'll see it, though, where it's written the same as the question you were given. So negative 3 is a normal multiplier now, so it stays on top. And because x has a negative 4 for the exponent, it can go to the bottom. 5, s equals t to the 3 over 2. So now we work with x and y most often, but you can really use any letters. I'm going to apply my my power rule. So 3 over 2 comes down in front, and now I have to drop it by 1. So 3 over 2 minus 1 is 3 over 2 minus 2 over 2, which gives me 1 over 2. And I'm going to match what's happening. I'm going to call this ds dt, because s is like my y and t is like my x. Okay, f at x equal to x. Well, you can think about this as x to the 1. So I'm actually going to apply the power rule to this. So f prime at x is 1 times x to the 0. But hopefully you remember that any base to the exponent 0 equals 1. So that just equals 1. So that's something to memorize, that whenever you have x by itself, the derivative is always 1. So if I have g at x equal to 7x cubed, now this is going to be my constant multiplier. The constant multiplier says the 7 just stays there and multiplies my derivative. So when I bring the 3 down in front, it's not going to be by itself now. I'm going to go 3 times 7 to get 21x squared. Okay, y equals 2x minus 1 squared. Well, we only know how to deal with an exponent when it is on the x, not on a chunk. So before I do this derivative, I'm actually going to FOIL this bracket. So if you need to, you can write the bracket out twice and actually do the FOIL. But if you know how to square a bracket by squaring the first, putting the 2 in the middle together, doubled, and then squaring the last, now my dy dx, this is going to be my difference rule and my sum rule, my constant multiple rule, my constant rule, my power rule. This is pretty much everything rolled into one. But I'm just going to do the derivative in pieces. 4x squared. 2 comes down, and that's going to give me 8x. 2 times 4, x stays. I drop the exponent from 2 to 1. The derivative of negative 4x is negative 4 times the derivative of x. Well, the derivative of x is just 1, so I don't have to write it. And this is going to be plus the derivative of 1, but because 1 is a constant, the derivative is 0, so I'm done at that point once I have the derivative. One more example. Okay, last lesson we looked at this, but the tangents are lines, so we can find their equation. So I'm going to find the equation of the tangent to f at x equal negative x cubed plus 3x squared minus 2 at x equal to 1. Well, in order to find the equation of my tangent, I'm going to use my modified slope formula, where I just need a point on the graph and its slope. Well, I have an x, so I'm going to use that to find my y. So f at 1 is going to be negative 1 cubed plus 3 times 1 squared minus 2. Now, this is negative x cubed, so it means to cube the x first. So 1 cubed is 1, then I take the negative 1 of it. That's going to be 3, and that's going to be minus 2, so that's 0. So I can put my point in right now. X is 1, so x1 is 1, y is 0. Now all I need is the slope. Well, the slope is found using the derivative, because the derivative represents the rates of change or the slope of the tangent. So I'm going to go back up to my function and say f prime at x is going to be negative 3x squared, that's power rule, comes down in front, multiplies the negative 1, I keep the x, I drop that by 1, plus 6x, 2 times 3, x, drop it 1, minus 0, because 2 is a constant, it doesn't have a rate of change, so it doesn't change as you put in different x's. And now to find a specific slope, because my point is 1, I'm going to figure out the specific slope at 1. So that's going to give me negative 3 times 1 squared plus 6 times negative 1, which is going to give me negative 3 plus 6, which is 3, or 3 over 1. I put that into my equation, and now I'm going to cross multiply. 1 times y, I don't need to do 1 times 0. 3 times x, 3 times negative 1. Then I write it in standard form, which goes the x term first with a positive coefficient, so that's why I let there. Then I'm going to do negative y, and then negative 3. So that is the equation of the tangent.